Hello, Assalamualaikum to honorable panels. My name is Muhammad Amin Mazmin Amin. My metric number is B02220036 and my supervisor's name is TS Dr. Nur Fatihah bin TSB. So my title is Iot-Based Water Quality Analysis System with ML-based feeding decision support. To begin, let's take a look at the problem statement that I aim to address. This is my problem statement. The first one is traditional system rely on manual monitoring and fixed feeding, causing efficiency, profit, health. And the next one is feeding system limitation. Existing feeding system operate manually on the fixed schedules, leading overfeeding and underfeeding, cause water pollution, fish mortality, and higher cost. And the last one is lack intelligent feeding decision. There is the critical gap for unified intelligent system that can accurately analyze real-time data, prevent feed output decision to ensure optimal resources fish health. Now let's take a look at the objective of my project. This is my objective. I have three objectives. The first one is to develop real-time IoT system using monitoring pH, temperature, and dissolved oxygen with telegram alert for abnormal water quality condition. The second one is to analyze historical and real-time sensor data using neural network-based machine learning model. The last one is to predict optimal feeding condition with at least 85% accuracy using historical and live data. Next is ability to address social design data. The first one is efficiency. The system minimizes to manual intervention by automating the water monitoring and feeding decision, allow farmer to focus on more critical aspect for management. This lead more efficient use time and resource and help the farm optimize farm operation. The next one is sustainability. The design supports sustainable aquaculture by optimizing feed use through real-time data, reduce waste, and minimize environmental impact. The third one is economic impact. By enabling data-driven decision making, the system has the reliability of feeding schedule, reduce operational costs, and improve productivity on farm. The last one is safe operation. By system use low power, affordable IoT sensor and cloud-based interface, ensuring safe operation for farmer with minimal maintenance. Now let's take a look at the methodology. This is my methodology. I have three phases. The phase 1 is hardware, the phase 2 is software, 3 is analysis. The first one is I conduct background research and I design system architecture. I use 3 sensor, pH sensor, temperature, and DO sensor. I calibrate those 3 sensors, and after I calibrate, I integrate this with ESP32 and I use OLED for display. The next one is I use Blink and I use Telegram to alert the abnormal sensors. And the last one is I use analysis, the phase 3. The phase 3 I use neural network, feed-forward neural network, and I use the feed-forward neural network machine learning to decide where they need to feed or not. This is my phase methodology. The phase 1 is hardware setup. The second one is cloud synchronization. The third one is machine learning model, and the last one is decision support. Now let's take a look at the video demonstration. For sensor data acquisition, in this phase, they have 3 key water quality parameter: DO sensor, temperature sensor, and pH sensor. For DO, the DO fluctuate between 4.17 mg per liter and 5.82 mg per liter, often close to the minimum recommendation level of 5 mg per liter. The morning DO reading are generally higher than evening, reflect oxygen production from daytime photosynthesis. Then the last one is the next one is temperature sensor. The temperature sensor is stable between 26.6 degrees Celsius and 28.6 degrees Celsius, which is optimal range for catfish growth. By the way, for information, I use catfish for to collect the data. And the evening temperature are generally higher morning, reflect the normal daily variation due to the heating from the sun. The last one is pH sensor. The pH value remains stable between 6.2 and 7.1, which is suitable for aquaculture condition. The pH sensor is not good and reading because the sensor is continuously checked on the water and become unstable. Next, let's take a look at the phase 2 monitoring result. For the monitoring result, I use Blink. The Blink dashboard display real-time data for the temperature, pH and DO sensor. The second one is Telegram. Telegram is the system to send this real-time notification when water quality parameter out of range. Take a look at the phase 3. The phase 3 is model performance evaluation. Key metric is precision, recall, F1 score and accuracy. The first one is for precision. Both no-feed and feed are class. The precision is close to 1, meaning the model predict feeding decision is very few false positive. The next one is recall. The recall is both feeding and no-feed is class is also close to 1, meaning the value identified near or the instant feeding or no feeding. The third one is F1 score, with the balance precision and recall is also close to 1 for both classes, or 100%. Indicated excellent performance. And the last one is accuracy. The model overall accuracy is 0.99, meaning 99% of the prediction were correct. Now let's take a look at the classification. The blue one is true positive for no feed, and the other one is 186 is for true positive for the feeding. This is ROC curve. The next one is ROC curve. The next is precision and recall for the test data, and the last one is for model performance for balanced data. Next is feeding decision prediction, actual versus predict, and the bar graph is for actual feeding decision, and the line graph is for predicted feeding decision. The graph show that the actual and predict are mostly the same, 99% of the accuracy for predicted and actual. Next is for feeding decision support and implementation. So I use Triplet to use the file upload and manual input. Enter the value for temperature, dissolved oxygen and pH value for manually, or you can just put the file Excel file for data result and predict the result. Next is sustainable design. First one is resource efficiency, SDG 12, responsible consumption and production. The system optimizes feeding schedule based on the real-time water quality data, reducing feed wastage and minimizing resource consumption in aquaculture. The next one is environment impact, SDG 14, life below water. By preventing overfeeding, the system help reduce water pollution, support cleaner aquaculture environment and contribute to SDG 14, life below water. Scalability, SDG 9, industry, innovation and infrastructure. The design is scalable for both small and large farm, allow the broader adoption and contributing to the sustainable aquaculture practice across various farm size. And the last one is cost effective, SDG 8, design work and economic goals. The low cost IoT system combined with machine learning provide an affordable solution, and sustainable farming help farmers optimize their operation without significant financial investment. Project conclusion and achievement. For the real-time IoT system, the system is successfully real-time IoT solution for monitoring pH, temperature and dissolved level. The Telegram alert will integrate to notify farmer abnormal water quality condition, ensure time responsible and potential issue. Data analysis with machine learning. The system achieved its goal to analyze historical and real-time sensor data using neural network-based machine learning model. The last one is prediction accuracy. The system was predict feeding over 85% accuracy both from historical data and real-time input. The data-driven approach allows system to make information decision when to feed, optimizing resource uses and reduce waste. That's all for me. Thank you.